Okay, yeah. So, as I said, sorry I missed class on Friday. I know you're all bitterly disappointed about it. And yeah, it's just we thought it would sleet, and we would come home, and it sleeted for 10 hours straight, and trees were falling everywhere. There was like on the way end of our development, there was like at least 10 spots where the trees had fallen on the power lines, 10 different locations in the same half a mile.
What part of
So,
Ohio were you in?
what?
What part of Ohio were you in?
It's over by Lancaster. It's called Hideaway Hills,
Oh, okay.
and it's kind of way out in the woods. And, it's nice, but when stuff like this happens, it's like you got to hang out, or else all your pipes will freeze, and you got to run the generator, or else you'll spend thousands of dollars getting your pipes repaired. So, anyway, but so yeah, that wasn't supposed to go on for so long. Okay, so I have put the old tests on the website just now, so you guys can go look at those. And as the saying goes, and the polymer people know this, there's beauty in struggle. So there's no answers on the keys on the tests right now. So struggle for a while, and I will put the keys up sometime over the weekend, I guess, and you guys can look at that. But you gotta look at the old tests, look at the notes, see what it is that you thought you knew you didn't know, you don't actually know. Okay, so go through that exercise and try to make a dent in the old tests, which I assume the polymers people think that works, right? It's not pleasant, but right, more or less. It's helpful. Okay, all right. Better than no old tests at all. Yeah. Yeah. All right. So have a crack at that. Today is the last lecture that will be on the test. So the test now, because of the snow issue, is going to be on Monday, a week from today. We're all still good with that? No conflicts? All right. Yes? Guys good? Okay. All right. Okay. So so what we're going to talk about today is a little bit about sintering practice, some more theory about sintering, but more of the practical issues associated with sintering. So we all know that sintering is trying to get rid of surface area, and we'll talk about that as well. But what we're going to delve into today is when things can go wrong, and they often do with sintering. It's it's a kind of a barely controlled process, and people still manage to make a lot of money off of it, but it's not something that is as under control as it should be. And so we'll talk about some examples of that here. But first, I'm going to talk about the driving forces again, in case you are at all unsure about this. And I know you can't see this well in your notes, but this is an array of what's called Stober process spheres. They're tiny silica spheres made by a particular chemical process. And as you can see, they're all the same. And they're all really tiny, which is kind of pertinent to what we're talking about in this class. And they're pretty much close packed. If you have the right level of dispersion, we all know about dispersions now and how we achieve them and how we attain them. Then you get these types of arrays of these really tiny silica particles, and you can use this to make opal, synthetic opal. Okay, if you're ever so inclined to make jewelry this way, you can. Opal is a similar thing. It's just nature makes it, and it takes a really long time. But we can do this synthetically. And the reason why I show you this is that we have this close packed array of particles, obviously close packed. And if anything, this should turn around and give you what you would expect, which is the equilibrium distribution of grains, right? You get six-sided grains in a perfect close packed array of particles. But in reality, you don't get that. You get this, all right? And as you can see, it's the same story. Now you've got several things going on. First off, you're not getting six-sided grains. Secondly, the grains are all different sizes, right? They didn't start out that way, but they certainly ended up that way. And then you see some are bigger than others, and so they're starting the process of gobbling up the little guys, all right, in this microstructure. Okay, and so even if you do everything perfectly, in terms of starting with spheres and heating them up, you're not going to get what theory might tell you should get, which is you're not going to get six-sided grains, and you're still going to have lots of grain growth as a result of the fact that not all grains are the same size. That's just an inherent part of the process. And so what's driving all this is something we can look at by just this little thought experiment in which we have an array of cubes, 6 by 6 by 6 array of cubes, which is going to total up 216 cubes total. And each of those cubes has an area of 6a squared, 6 sides, all right? And then we think about gamma as a driving force for this. And for this particular experiment, what we're doing is we're defining gamma for the surface itself as being 4 joules per meter, and for, as you'll see, the grain boundaries, 1 joule per meter, all right? So we're throwing in some numbers, and these are kind of realistic in terms of how things scale in real processes. And so we start out with this array of cubes, and we have gamma sub s, 4 joules per meter, is the driving force for this 6 by 6 by 6 array. And if we look at the math for all this in terms of a squared, it's 5,184 joules per square meter. And that's just sitting there floating in space, by the way, they're not touching each other. And now we bring them together, and we make a cube that's not going to be floating in space, individual cubes anymore, but now it's an assembly of them. And we still have 216 of these cubes in this array, and they still have a surface area of 6a squared. But what we're doing, first off, is we're not looking at gamma sub s anymore. Sorry, I can't talk to you now. You should have called earlier. Gamma sub s has been replaced by gamma GB. All right, so we made these grain boundaries by putting these cubes together, and we also have half the amount of surface area because now they're sharing those a squared areas. Okay. And so that in itself has allowed us to go from 5,148 or 8, whatever it was, 84 to 648. So already we've dropped down the surface area quite a bit just by bringing them together and going from solid surface vapor interface to grain boundary interface, where two grains are looking at each other across this interface. And we've done no grain growth in this simulation. So there's a huge driving force just to get rid of surface. All right, that's what this is about. And then we finally allow grain growth to occur. I just put it in quotes because they're still cubes, which is crap. But what you've got now is a 3 by 3 by 3 array instead of a 6 by 6 by 6 array. And so what we've done now is made this 27 times 6 times 2a squared, because now they're twice the size of what they were before. Still 0.5 times GB, and it's now 324 a squared joules per meter squared, and it's actually 16 to 1 driving force, and so more than 10 to 1, 16 to 1. And so there's a huge reason for this to turn into that. So first off, a huge reason to become grain boundary interfaces rather than surfaces, and then another driving force is to get rid of those guys, all right, and reduce the number of grain boundaries in the system. All right, and so this is just what drives this process forward, reducing the surface area, curvature, high temperatures allowing mass transport, allowing for the growth of grain boundaries as they jump across that concave convex barrier, and grain growth is achieved. All right, and so this is just to give you a good idea of what happens in these systems, and it is energy driven. And the example of that is if you take some of these nanoscale arrays and you drop them in the furnace at 1500 degrees, their temperature will go above 1500 degrees because you're liberating all that energy, and it shows up as a temperature increase of the mass. It's a terrible way to make a ceramic, but anyway, it is just showing you that there's energy locked up on these surfaces, and that energy can be liberated when you undergo these microstructural changes. Any questions about that? That should all make really good sense at this point, hopefully. And so we know, just to review, we know there are different pathways for this. This is this classic three-sphere Ashby diagram, in which you've got different things going on that involve vapor transport, surface transport, transport within the solids themselves, and the one additional wrinkle he has is those are supposed to be dislocations that are moving things around. In ceramics, their dislocations are of no importance whatsoever, except for maybe MgO or something like that. But it's just one more pathway to move atoms around. And so this is what we're looking at, and again, we're really concerned about this center-to-center distance, all right, or the center of the joint between the two. and what are those distances, and how can we make those distances shrink. All right, we want the spheres to come closer together, which means the whole thing is now densifying. All right, and so what we've got is a series of mechanisms, 1 through 6, surface diffusion, lattice diffusion, vapor transport, boundary diffusion, lattice diffusion, the source of the matter and the sink of the matter. All right, and you see the sink for all of them as a neck. All right, you want to put stuff in that neck to take advantage of the fact that it's a concave area. And we have 6 of these, which mechanisms actually allow for densification. Anybody want to guess? Or which don't? Maybe we'll start there. It's an easier thing to answer. Which don't allow for densification, which don't lead to densification of those 3 spheres. Which number? Give me a number. 2. Okay. Yeah, so 2 does not allow. You're taking it from the surface and you're transporting it to the neck, but you're not shrinking the space. So you're taking surface and putting it into the neck area. All you've done is you've made that surface smaller, but you haven't caused the spheres to come closer together. Does that make sense? All right, and so on that note, we also have surface diffusion from the surface. So it moves along the edge here and ends up in the neck. All right, it's happening all over the place. All right, none of those are causing those surfaces, the center of those spheres to come closer together. And the same thing is also true for vapor transport. If it goes out into the vapor and then sits down in the neck, that's not causing those spheres to come closer together. You're eroding the surface, but you're not bringing those X's, those crosshairs, closer together. All right, does everyone see that? And the only ones that are 4, 5, and 6. And so we're diffusing along the grain boundary, and in doing so, let me go back to this overall picture. If you're diffusing along the grain boundary, let me clean this up a little bit. Diffusing along the grain boundary, which has just been formed, right, by the way, and you're going to that neck, all right, you're taking atoms away from that space between those crosshairs. And so now these X's are getting close, the crosshairs are getting closer together. All right, you're just shrinking that distance. And so that's an efficient densification rather than inefficient densification. So everyone see that, hopefully? All right, so it's just a matter of getting atoms out of that space between those crosshairs. And the same thing is true for lattice diffusion, because it's going from the lattice, from the grain boundary along the lattice, meaning the solid diffusion, volume diffusion, and going to the neck. And then we also have this weird one, dislocations, which also allow for transport toward the neck area and removing matter from the pathways in between those 2 crosshairs. Okay? Does that all make sense? So not everything that's going on in these systems is achieving our goals. It's achieving its goal, but it's not achieving our goals of trying to minimize the energy of the system. And so there's a bunch of different ways of looking at this. And the only reason why I'm inflicting this 2-sphere model on you again is to show you that, remember, that they touch, the neck forms, and the grain boundary also forms. All right. If each of these particles is a single crystal, then there's only one grain boundary. If each of the particles is multicrystalline, which is kind of normal actually in the scheme of things, then you have many grain boundaries forming as those necks form. All right. So it may not be just one grain boundary, but the point of this is that this is where I would like to go. All right. It wants to take all that matter and eliminate that surface area as efficiently as possible and turn everything into a darn big sphere. All right. Do they still teach about spherical cows in physics? No? Not talking about spherical cows? Okay. All right. Anyway, it's one of those interesting discussion items. If cows were spherical, anyway, and you can see this. You can see the initial stages of this. This is in some particles when they're nice and round. You can see the next form when they contact. All right. With ugly ceramic particles and ugly metal particles, it's hard to spot these necks. But when they're nice and round, you literally see exactly what you expect to see from these cartoons. And keep in mind that, again, if each of the particles is a single crystal, which is not always the case, but does happen, you have one lattice with atoms arranged in one 3D array looking at a second lattice that's arranged in a different orientation. It's the same crystalline lattice of the same material, but because they're oriented different, you must have a grain boundary show up between them as soon as that next forms. All right? Make sure you are totally aware of that. And we could look at this in 3 dimensions, and you sort of saw this in the simulations. All right, as they first touch, they form those grain boundaries and they start to move toward each other, and then later on, as they form more and more of these interfaces and they become more mature, then you start to see the pores that remain and so forth in these different vertices. All right, so that should all be kind of clear at this point, hopefully. Any questions about that? Related. This guy, that grain boundary, that is a region of local atomic disorder, right? Remember this, or a series of Schottky dislocations, or there's various ways of describing it. But it's not very well organized. And because it's not very well organized, diffusion in there is much faster than it is over here. All right? And so that we like to go. And then we talk about a couple of other things. And so we have this this surface diffusion and grain boundary diffusion and lattice diffusion, all of which are going to the same place, moving atoms around. And we have, getting a little more advanced here, we have the initial point contact where they first touch, and it gets rid of that point contact as quickly as possible to cause a grain boundary, which replaces gamma sub s with gamma GB. The system likes that. All right. And then the thing that is the macro scale here is that all this is going on. What happens to the system in terms of the connectivity of these pores? And so we know that initially all these spheres are surrounded by empty space, and we form a grain boundary, but we still have this empty space. And that empty space consists of tunnels that go all the way to the surface. All right? And so the beauty of that is, as this thing starts shrinking, as this distance finally decreases, then the air, and that turns out the air or atmosphere, whatever it may be, turns into our enemy at this point. And so we're trying to get this air out, because the air is what sits inside those pores. And you want to try to get this out, and when these pathways, these pores are continuous, it's like squeezing a sponge. Air comes right out. All right, just no problem at all. But then, and you'll see this somewhere around here and certainly there, those pathways of the surface get cut off. All right, everything keeps shrinking and shrinking and shrinking, and eventually the pores are isolated. And then that nice pathway of just squeezing the sponge and getting the air out stops. All right, and then at this point, diffusion rears its ugly head. So we can no longer squeeze the sponge. We have to rely on diffusion to get this out. Diffusion, again, slow. All right, we don't always think of diffusion as slow, but there are different types. All right, and a couple things can happen. Let me erase that part, and it shows you this here. We have pores in a couple of different places. This is a pore, and we've seen these before. It's on the inside of the grain. All right. And then we have a pore that's on the grain boundary. All right. And so the thing that I want you to keep in mind is the grain boundaries are pipelines to the surface. And I guess I could say diffusional pipelines to the surface. All right, but they're what we're stuck with when the sponge stops. We lose that connectivity of the surface, the porosity with the exterior surface. We're stuck with diffusion. And of the two choices we have grain boundary-based diffusion, where these things just move along the grain boundaries and eventually find their way. And when I say things, of course I mean air, if we've done it in air. So we have oxygen, diatomic oxygen, diatomic nitrogen, and what happens is those guys go from being diatomic molecules to being ions, and they migrate out as ions, which is why it's one of the reasons why it's so slow. All right, and so they diffuse along those grain boundaries, and obviously that's not as good as the sponge, but what's even worse is when this guy is not on the grain boundary. All right, so then we have the worst kind of diffusion for us is volumetric diffusion, or lattice diffusion, as it was defined in those tables, meaning that it has to exchange a vacancy or a nitride, a nitrogen ion or an oxygen ion with a neighboring atom, and those two kind of do the little dance, and eventually it gets to the grain boundary, and then it can diffuse to the surface more easily. All right, so if you recall, I showed you this image. Oh, great, now that's all just going to be that. We like the fact that it does that. That allows us to get these gas atoms out more quickly. And if a grain leaves a pore behind, leaves it in the middle there, we're stuck with this annoying, there it is, we're stuck with this annoying volumetric diffusion, which we don't like. Very slow, very expensive, high temperatures, long times. Your boss is not happy. You're spending more money on energy costs than you should be. Okay, and so that is a big driving force for a lot of operations in this area. And get this out of the way so I can talk about this image. This is showing you an example of this, and it's a very easy example. Unlike ceramics, you can take nickel and a lot of other metal particles and squish them in a die. And you pop it out of the die, and it's this shiny metal cylinder. You can throw it against the wall, and it doesn't break because it's these nice metals. All right, they're so easy. So, but if you cut that nickel compact together, then you see there's still plenty of pores. All right, so it's not water. It doesn't squish out all the porosity completely. It leaves lots of pores behind in between those original particle interfaces. And if we start heating this up, a couple things. You can see that we've got lots of pores left, and you can also kind of sort of make out grain boundaries, I hope. You can start to see the lines there that constitute grain boundaries. And this is all indicative of all this grain growth that's gone on. These guys started out a certain size, they've grown, and you've got pores left too, all that dark stuff. And where you want those pores to be, of course, is on the grain boundaries, and it's kind of hard to see anything here. You occasionally make it a grain boundary, but lots of dark pores. And then as we go toward what they call the final stage in this context, that's where you see success and disaster. So you see some pores sitting on the grain boundaries, doing what they should do, diffusing the contents toward the surface, but then you have others that have gotten put inside the grains. All right, so if you let this sit at temperature, what you'll see is those pores in the grain boundaries will disappear, whereas the pores in the middle of the grains will still be there. You'll still be able to see them. All right, and that's a measure of how much more efficient diffusion along the grain boundaries is versus diffusion within a grain. So everyone follow that? Okay, so you want grain boundary surface area is what they call it. If you took this thing and blew it up into all the different grains, you'd have a certain surface area associated with that collection of grains. And you want that to be as high as possible, meaning that you want the grains to be as small as possible, so you have as many pathways to the surface as possible, so you can get the best densification you can possibly get. All right? And the whole process of grain growth frustrates that because it gets rid of grain boundary surface area. It eliminates it, all in a pursuit of minimizing gamma GB. Okay? All right, and that is the way it is. The system does that. We know how to slow it down, but in many cases we can't stop it. And so then we have to think about, well, if we do get grains with pores inside them, interior pores versus grain boundary pores, again, as I said, if these two pores are sitting there and we come back later, you'll see the grain boundary pores gone because it diffused to the surface along that pipeline to the surface, as I always like to call it, to give you a clear idea of just how efficient it is versus the interior pore, which might still be sitting there in the same microstructure. All right, because it's stuck with just slow volumetric diffusion. All right, and so again, think about this as grain boundary surface area, and this is again another benefit of small grain sizes. If we can keep our grains submicron, then this whole process of eliminating pores becomes much more efficient, meaning that our defects become smaller or hopefully absent, is where we're really driving at. No pores at all. In most cases, they're not successful, but you make the pores small when you make the grain sizes small, and you try to resist this process of grain growth, which is fighting us in terms of our desire to get away from this entrapment issue, pores on the inside of the grains. All right, any questions about that? And there's this, I just feel obligated to show it. There's a thing called Herring's scaling law. And what Herring did was he looked at these two particles as two characteristics: the size of the particle, the radius of the particle, and this variable x2, which is the distance from the center of contact to the edge, meaning that it starts to diffuse out, all right, and get away from this whole area. And so you look at that ratio of x to r, and it's supposed to give you some idea of the degree of sintering in the system. And then if you do that as a function of time, then you have x sub r, x divided by r divided by t, that gives you the rate of sintering, okay? And so the larger x is, the faster the rate of sintering is. All right, so that's all part of this process. But the whole point here is he developed a law, and there's a huge amount of activity to actually make it predictive in some way, and it all failed spectacularly. But anyway, Herring's scaling law says that the rate of sintering for two different particle sizes is equal to this ratio of R2 to R1 to some value of P, 3 or 4 depending on the fusion mechanism. And the point being that if you have R of 1 micron, the time of sintering is 100 seconds, whereas if R1, in this case, is 100 nanometers, the time of sintering is only 0.01 seconds. All right, so that this law becomes useful in terms of providing some useful simulation of time involved when these diffusional processes are happening. And so when R is small, and you guys saw this in that crappy hot stage microscopy video, if you look closely, it's all at the beginning. When you start with these initially small particles, they almost disappear instantly, and you see grains show up that are way bigger than the original particles. And so that's what's going on, is the small particles grow instantly almost and become larger particles, and then the rate of change slows down a lot because the particle size now is larger. And so you see this, the impacts of this, in terms of the use of the nanoscale in ceramic injection molding, and you worry about things like agglomeration and what kind of drag forces are necessary to get to these types of microstructures, which are pretty good. All right, so we have this 1/7 rule, different particle sizes. We've formed compact. We remove the binder. You guys know about that now, and we start to sinter it. And I just want to make sure so you form the necks, and it starts to look like a sponge at this point. All the particles are gone. They're all glued to each other. A lot of the porosity that was still there is still there. So this is still a sponge-like structure, and the air will come out easily. But it won't take long for this to start sealing off those pathways, all right, and providing barriers to further densification in these systems. But we have to engineer this thing on the left-hand side, and then hopefully what happens on the right-hand side is more efficient because of how we engineered it. All right, and so that is why we spent so much time talking about that, because if you do a good job on the low temperature stuff, then the high temperature stuff will take care of itself. All right. The one consequence of the fact that we're dealing with these different particle sizes, deliberately different particle sizes, is that the fine particles can be difficult. So if you've got something that consists of large particles and small particles following this roughly this 1/7 rule, then they start to form bridges with each other, and these bridges start to prevent motion, all right? And so if we're applying force, which is what these lines are, then that force becomes more difficult because the presence of these fine particles helps glue everything together and make motion more difficult. And so this is an additional challenge we faced because of the fact that we have created this 1/7 rule and we try to follow it. And again, so a lot of this is like, well, we had a set of guidelines, we did the best we could, and now we have all the consequences of these things that we developed, that we tried to give ourselves 80% dense solids, but now we have all these little bridges forming because we made these 80% dense solids. So that can be a problem. Before I move ahead here. Yeah?
What is the 1/7 rule?
So it's where we have, if a particle has a diameter of 1, then we want to find particles that are 1/7 that diameter to fit into the spaces between all the 1 micron particles, right? And then you can take it further and end up with 1/343 of the particle size to fill in the spaces inside the other particle sizes, that kind of thing. So it's 1/7, 1/49, 1/343. Remember all that? All right, so this, and we hardly ever go beyond 1/7. We certainly don't go to 1/343. Some people do go to 1/49. But anyway, that's just the general idea of putting fines to take up spaces between the coarser particles. Any other questions? All right, but there are consequences. There's always consequences. Very complicated systems again. Okay, any questions about it? It's amazing we make money off of this stuff. All right, and so then we have liquid phase sintering, which, based on what we just talked about, probably seems like a huge relief because we can form a liquid that fills up all those pores, all right, and makes this process of transport much more efficient. But you might remember when I talked about liquid phase sintering at the end, you pay. You have a more efficient densification of a system, but you end up with some degradation of the properties. And the other side of this is that not every system has a liquid phase that works to sinter it. All right, certainly not without degrading its properties. So some things work okay. Not every system can be liquid phase sintered, but when you can do it, it's awesome. So this is showing you solid state sintered yttrium aluminum garnet. Let me know what that's used for. All right, so these are used to make lasers, those little tiny 610 nanometer lasers. Did you make a guess about lasers? All right. No? You counted?
Countertop.
Oh, counter. Well, granite. I mean, it's a component of granite, so yeah, it is in countertops, but they're not pure YAG. But anyway, yeah. But this is a very useful system, and you like it to be, as you see here, pretty darn dense because lasers work better that way when they don't have pores stuck inside of them, and so you can use this to densify these things. And when those liquid phases are present as little particles, they melt. They allow grain growth that you're kind of seeing here. When we go from 1, 2, or 5 particles, blue particles, to 3 blue particles, they've gobbled each other up, and they've also moved around. And the capillary pressures that develop in this liquid phase here that's what causes it to move around and try to occupy space more efficiently. All right, and so that is hard at work in giving us improvements in densification. You get this process of densification at lower temperatures because you're not relying on liquid phase. You're not relying on vapor phase transport anymore. Now you have liquid phase transport, which is way more efficient, and you have liquid phase, which doesn't go away. All right, so you have plenty of diffusion going on inside that liquid. All right, so we don't have to worry about pathways to the surface because the liquid forms a permanent pathway to the surface. And so you can have lower temperatures, robust processes, but of course the downside could be poor properties. It depends on what it is you consider poor properties. And the example that I always like to give is porcelain. All right, and so we all live our lives around porcelain in various ways. And porcelain is made by liquid phase sintering of, we have mullite, which is a silicate aluminate, corundum, which is alumina, different types of mullite, some quartz. All this stuff gets sintered together with a liquid phase, and we spend our lives eating off of it and sitting on it. So it works pretty darn well, even though it's a liquid phase sintered process. Of course, we're not going to put a ton of stress on these things. All right, you're not going to try to stand on your porcelain plate. You know what happens if you do that. All right, so there are limits to what it can do for us. But there are some stunningly good examples of where it's important. And this is one example in which we are working with silicon carbide, and you see here two different compositions involving silicon carbide and different amounts of YAG. So I just talked about YAG as a solid state and how it's useful for lasers. You take that YAG, you heat it up a little more, it becomes a liquid, and you can use that liquid to densify silicon carbide, which is even way higher temperature melting than YAG is. All right, pain in the neck to work with this, more energy required to densify it because it's got such a bloody high melting point. And this is just showing you at 20.0 concentration of YAG, 3.1, we have these whisker-like shapes of silicon carbide, but if we go to a slightly different concentration of YAG, and now the silicon carbide has turned into nice grain-like shapes. We like this, all right? This obviously will densify much more efficient under gravity than the one on the left, okay? So hopefully that's obvious that the one on the right is going toward an efficient grain boundary-based structure. We still have that liquid phase around it, so it depends on what you're going to do with this silicon carbide, all right? But something that is kind of one of those hidden things in technology is machine tools and cutting tools in particular. And cutting tools make use of one of the hardest substances known to man that can be commercially used besides diamonds is tungsten carbide. All right, it's got a melting point of like 2850 or some crazy number, which is even higher than carbon. So it's really, really a pain to densify. And so what they do is they take tungsten carbide and mix it with nickel, and you compact that into shapes. Remember, nickel is nice and soft, so it kind of helps out in that area of things. And then you heat it up. And so what you've got here in this image is tungsten carbide particles with the nickel liquid phase all around them. They've rounded out nicely, transport's occurring, and then you cool it off, and you have this really good tungsten carbide cobalt system that is used to make $1 billion at least a year in cutting tools. All right, specifically for machining titanium and cobalt chrome and aerospace alloys and all sorts of things. Great for that. Tiny little black triangles. If you ever go to a machine shop that's working with that, they have tons of these, and they go through them, by the hour. But for machining these metals that are really hard, tungsten carbide is the only way of trying to work with that. And I have a video, not today, but in upcoming lectures in which you'll see one of those things at work. All right, so when it works, it's awesome, but it's not available to everything for everybody. Okay, so, in most cases, sintering temperatures vary between 1400 and 1650. All right, if they can you can get there cheaply, that's awesome. Total sintering time can vary from several hours for small parts to several days for really large parts. And the majority of this time is taken up in gradually heating and even more gradually cooling the sample. So we always think about sintering as that high temperature point, but a lot of the time involved is that slow crawl up and the slow crawl down. Initial rate of heating should not exceed a critical limit. So we talk about fast firing, but even fast firing has limits. You don't want to create internal stresses. If the melt needs to form for liquid phase sintering, that takes time. It can be a chemical reaction that takes time to happen. And so all these things need to be considered. And there's the other factor in that we know that sintering time and temperature can always be decreased by increasing the temperature itself. So your boss says, hey, I don't like the fact that it takes 5 hours. We want it to take 1 hour. Well, let's crank it up to 200 degrees. And yeah, maybe it will take only an hour. But it can lead to excessive grain growth or abnormal grain growth. And that's shown here, in which we have kind of on this side of things, it's okay. But then over here, what we've done is we've got this giant grain that's gobbled up all its neighbors. And even worse, it's generated all these huge internal pores. So you can't just throw more temperature and money at it and solve the problem. All right, you can only make the process go so fast. And too much liquid phase is the wrong liquid phase, and that's shown here. This is X-ray data for this particular YAG-based system involving silicon carbide, like you just saw. And at 1925 degrees sintering, we have stuff we want. We have YAG, silicon carbide, this YAG aluminide silicate. But if we go just 25 degrees higher, then we have things that we like again. We have the ag, silicon carbide, but now we have formed this carbon-based compound, and that carbon-based compound dissolves in water. All right, not a good thing for a ceramic to have something inside of it that dissolves when it sees water. So that is a disaster, and it happens with a very small increase in temperature. All right, so these things are like chemical reactions, these ceramics and a lot of the metals as well. Okay, let's see. And we also have cooling issues, which is one of the really annoying things, especially in some large parts, like a lot of these aerospace parts. You can have something that cools up or heats up, and you let it sit there and densify, and then you cool it down, and what happens is, let's go back to those numbers. Say we're sintering at 1950 C, which is not out of question, and we start to cool it down. So our furnace is now at a relatively chilly 1800 degrees centigrade, all right, because we've shut the furnace off or we started to ramp it down. And so what happens though, ceramics, as you should remember, are lousy thermal conductors, all right? They don't lose heat very well. And so what will happen is the surface, everything is still, I mean, both of these temperatures are white hot to our eyes. You can't look at this stuff at these temperatures. But anyway, the surface may be, let's just make it 1850, and then another gradient in from there might be maybe in this thin area 1900, all right? But the center is still 1950, all right? Because it's a lousy thermal conductor, all right? And so that means that the surface is trying to shrink, and the center is saying, no, I'm not going to shrink because I'm still the same temperature I was before. And so as that surface shrinks or tries to, that creates a tensile stress on the surface. Again, it's a consequence of the poor thermal conductivity. And so if you have a flaw present, a pore of any kind or contamination or something, then what you've done is you've created a bunch of thermal or tensile stress. And if that equals 1 here, a nice flat part of the surface, here at the defect it can be 10. All right, concentration of stress at that defect can drive fracture based on that defect. So you can slowly cool it down, and then you hear a inside the furnace, which means that your part has self-shattered during the cooling process. All right, so you can't go too fast in these systems, no matter what your boss says. All right, you can go slower and end up with product as opposed to not having product. Everybody get that? The tensile stress development should make sense when you think about it. The surface is shrinking. It has to shrink because it's cooling off, and the interior is not because it isn't cooling off. Okay? And that causes these problems. And this can interface with things like grain boundaries. And this is where grain boundaries can be a weak point because it can tear apart a grain boundary too, as well as a pore. All right, so in this context, verification of mechanical performance is very critical here. The things that we like about ceramics, the fact that they're very wear resistant, they don't generate too much particle when they're articulating against themselves. They're very hard, chemically resistant. All right, alumina lasts at the body. It doesn't really do much to it. All those things also make it very flaw sensitive. Presence of defects in the microstructure or on the surface, as we just saw. And we need to get some idea of the mean failure strength of a component under stresses. Let's call it uniaxial stress. And we also need to, very importantly, develop, a very firm estimate of the inherent variability of these parts. All right. And so I just reprised this image of what happens when these things fail in vivo. All right. This does happen, and we want to know. We know why it happens. We want to minimize the fact that it happens, but we want to also account for the fact that we know it's going to happen and try to make predictions about these things. And so what we do is we first consider what's going on in these systems. This is on this other image. This is showing you a nice metal with a flaw in it, and when it reaches a certain stress on that flaw, what are these things that shoot out from that defect? The word most ceramics people don't like. What do metals do when you stress them? They create Dislocations, exactly. All right. So you're seeing a ton of edge dislocations shooting out from that flaw, and it's accommodating all that stress. And that's the difference between the metals and ceramics, is that metals can do this, and it's still one piece. All right. You shot all these half planes here and there and everywhere, but it's still in one piece. It has not failed. With ceramics, you have, unfortunately, again, the very sharp flaw, and these atoms will peel apart at about a 15th of the modulus, meaning that this crack gets going and then it moves speed of sound after that. And that's how these things break like glass in vivo, because there's just so much energy involved, and there's no resistive mechanism. It doesn't generate dislocations, unfortunately. And so these flaws, as I keep hammering you with, are deadly, more or less, depending. They literally could be deadly. And we have to think about what causes this. We know their flaws. We have size, shape, location, and size distribution is important. They're not all the same size. Some are bigger than others. We look at predicting fracture stresses in the presence of known flaws and machine defects. Remember, we have to shape these things, and so that can also generate defects. Fracture is far more sensitive to flaw characteristics than anything involving the surrounding microstructure. Final flaw size can be affected by changes in grain size. Solid contaminants can affect the strength. Differences in thermal expansion coefficients between one phase and another in a ceramic can cause cracking. Differences in elastic properties can reduce cracks when a load is applied. We've seen the consequences of that. Whoops. And the ceramic injection molding connection between processing, fabrication, and flaws is difficult to understand, let alone control completely. So I hope you have the impression that this is a complicated process, densifying these things. All right, it's not like a nice liquid. And so what we do is we estimate. Process is always destructive. We do modulus of rupture. This is a 3-point bend test. Over here is a 4-point bend test, which is definitely better. We can't really do what is done in metallurgy and make dog bones out of ceramic. Just can't do it. It's too hard. All right, but what we can do is make flat surfaces and stress them with 4-point bends and 3-point bends and generate these modulus of rupture loads or mechanical strengths for these systems. And it's always destructive, meaning that we lose that part, but hopefully it came out of the furnace with 100 other sister parts, and what this one part that is destroyed will do is tell us something about all the sister parts that came through the same furnace. Surface, as you see here, this surface is we're trying to stress that surface. Now, it's a ceramic, it doesn't visibly bend, but we know we maximize the surface stresses on. All right, and so the strength of any set of samples depends on both the maximum stress and the distribution of stress. 4-point bend tests, because they tend to focus the stress, not just through the whole microstructure, but on the surface of the opposing side. And so we get a better idea of what's being stressed, where the flaws are coming from, and so forth. And the strength of these components, this is showing you for a couple of different kinds of alumina, different values of strength. I'm going to talk about that. But what we do is we design for failure. All right, so these Biolox alumina parts, they have a failure rate of 0.004%. All right, so that means that if you get one of these things in your hip, you have a 0.0004% chance of that thing failing. So out of 1,000 parts, maybe 4 will fail. All right, maybe. Okay, and so what we do, we incorporate safety factor. We do a ton of work on modulus of rupture, and we see that the wider the scatter, the less reliable the material is. I'll show you an example of that in a second. So we have 1,000 parts. Assume we break them all. All right. Some will have a high strength, some will have low strength. The majority will fall in the middle of that Gaussian. And what we do is we measure something called Weibull modulus to estimate the probability of failure. And we assume there are always flaws in the system. There are always flaws in these systems. Grain boundary is nothing else. And then what we say is the weakest link is what leads to failure. So the largest flaw is revealed, found out, discovered by that stress, and that's where failure takes place, is that largest flaw, wherever it is in this area that's being stressed. And so we have these nice Gaussian distributions, all right? So over here, things are good, all right? We like those. All right, but over here things are bad. All right, those are the ones that are going to be the 0.0004% failure rate, and then the majority of everything else is over here. So basically, what we do is, we hope for everything on the right-hand side, and deal with the consequences of what's happening on the left-hand side, and that may be that we assume that something's going to fail, and we have a legal representation necessary to be sued, essentially. And it's a very straightforward process once it happens. But they'll pay for the cost of the revision surgery and all that good stuff. But anyway, but this is just showing you what this Weibull modulus data looks like. So for specimens of volume V0 that survive under tensile stress, external tensile stress of sigma, we have this PS equals this EXP value, where this sigma sub naught is not actually a stress, it's a scaling factor. And these exhibit a slope m, which is called the Weibull modulus. And if we have a lower m, that means we have a greater variation in strength. Chalk, which we don't have anymore in here, is typically about 5. Steel is more like about 100. And what we do in the context of manufacturing is periodically reestablish what that Weibull modulus is. And so we break 1,000 parts, and we see that for chalk, it's got a pretty low value. Steel's pretty good because it's got those wonderful dislocations that make it easy. All right, but engineering ceramics are more like 10, and of course the more vertical we can make that data, the better off we are. But this is what we do to figure out what's going on, and you have to redo it every once in a while, because who knows what's changed. Maybe your parts have some kind of contamination, and you don't want to let those go out the door and go in somebody's hips. All right, so you got to keep doing this over and over again to figure out, are we still at 0.0004% failure rate, or has it crept upward somehow? In the case of zirconia, it crept up a lot. And we also do NDE, and there's a bunch of ways of looking at this. You can see relatively large defects, and we talked about X-ray CT. I'll show you that in a second. Ultrasonics is one other technique that's been used, usually only able to see relatively large defects, interfacial defects, but it does work. So TOSO SMD down in Grove City has one of these things. One of my former graduate students is in charge of it, Jeremy Gomer. And so this can be used to find relatively large flaws. We also use X-ray CT, and X-ray CT is wonderful stuff. Good resolution for detecting smaller flaws than ultrasound is currently capable of. It's also non-destructive. All right, it doesn't shatter the part like MOR does. Modular rupture, you have to break the part. But with X-ray CT, and these are some examples of silicon nitride airfoils, you can scan these things internally and get an idea of the flaws, how many of them there are. There's a concentration in the middle of this one, for example, all right, that might be of concern. And how that relates to the process, it's very complicated, but that allows you to look at these things. And this is just showing you a couple of injection molded ceramics made from slip A and slip B, which refers to the liquid. They're both injection molded, and you do an X-ray scan on them. They look the same. You don't really see much of anything, but then you remove the binder, de-waxed as it says here. Then you see a bunch of cracks show up in slip A, and only a couple cracks show up in slip B. All right, so this is the kind of thing that you can use to say, all right, well, there's a problem with slip A. We need to go work on that. All right, but so NDE has the potential to solve all our problems, but because we're so good at making flaws small, the flaws are too small for X-ray CT to see. All right, so unfortunately, and that's the dream, is to be able to scan every single femoral head that goes out of the factory. But right now we can't do that because we can't see the flaws. They're so small now that the technique can't resolve things that are that tiny. All right, but that would be the goal ultimately, is to have no flaws that worry us at all from any part that goes out of the factory. But until then, we're stuck doing these modulus of rupture, Weibull modulus determinations, knowing that we have variances in the manufacturing that lead to less than ideal values of failure. But predicting that and owning enough lawyers to get you around that when it happens is the current strategy. Okay? Any questions about all that? We're all good to go. Test a week from today. All right? All right, let me know if there's any conflicts with that. Otherwise, I will see you guys on Wednesday.